Oh, this is flickering a lot. Okay, so today I want to do something a bit different. There's no calculations today. Okay, so let me just go through what we kind of did. So we started with some very qualitative estimates of scales. Okay, that were, or in my opinion, rather informative to, yeah, it's flickering a lot, yeah. To kind of drive and motivate what we were doing. Then we suffered a bit and we got to write full resummed propagators in the medium. So propagators that take into account all possible interactions with the medium. From that, we were able to build some, I know what's happening. My computer is echoing. No, it's even worse. I have the sound up, so. Okay, we built some effective in medium Feynman tools so that we could use our propagators in Feynman diagrams. Okay, and then probably where we suffered more, we carried out the single gluon emission calculation. Okay, and the result was something that resembles that thing on top there, which after much suffering was actually not too complicated. Okay, these P dot Q, so these are the momenta, sorry, the momenta that exit the vertex of the quark and the gluon. This thing accounted for, that is written here, accounted for whatever happens during the formation time of the gluon. So when in diagrammatic form, the gluon has been radiated from the amplitude, but has not yet been radiated from the complex conjugate amplitude, which means that it's not a physical particle, okay? So it had this fancy path integral that we can only hope to solve once we specify what that potential is. And because our ability to calculate path integrals is more or less restricted to Gaussian integrals, it's more or less obvious that if I don't assume something quadratic there for the interaction potential, I'll never be able to solve it in closed form. Okay. And then, so this is what happens during formation time. And then after formation time, up to infinity or wherever the medium ends, what I have is some sort of just classical broadening, okay? So there is no kinetic term, so there is no wobbling in position, but I keep on interacting with the medium. And who keeps interacting with the medium is this gluon that has been radiated. Okay. So many options, okay, that I listed yesterday. I wave my hands, believe in things, and find the motivation to write this as a quadratic potential. So the so-called harmonic oscillator approximation or Q-hat approximation. And I do the calculation in closed form and I get a result. And that result is good or should be good in regimes where what dominates are multiple soft interactions. The result by construction has to fail whenever an exchange, an interaction with the medium is sufficiently hard, because quadratic potential lacks momentum to the fourth tail. Okay, so I'll never get it right for things that are significantly hard or hard enough. Okay, another possibility that I have is that I expand this order by order in the number of interactions, and then I know how to do it because actually the path integral will be just of free things, and the potential is localized somewhere once. And at the end, I have to integrate over that position, which is arbitrary. Okay, so that's the so-called opacity expansion. that I can be very brave and go to second order, considering 2 interactions, third order. I think there's calculations that go up to 7th order. But it's being brave, okay? That calculation, in particular the n=1 opacity calculation, should be, so it has, I can use whatever potential I want. It should be correct in regimes where everything is dominated by a single interaction with a medium, or a single effective interaction with a medium. Okay, so let me call that a dilute medium. So there's my probability of encountering things to scatter with is small, and the other approximation of the harmonic oscillator when my probability of encountering things is very, very large. Okay. Now, can I do better? Yes. Actually, I can do it for whatever potential I want. So there's something missing there, and it's a shame on these things here. The first one is, you'll recognize as some sort of Yukawa potential. Okay, that's good. It's one way of modeling the interaction of the parton with some screened color charges in the medium. But even better is this hard thermal loop computation, which is a similar computation, but a bit better. Okay, and there the screening mass is this debye mass of the medium constituent. Okay, so these potentials, if I try to solve the path integral, forget. If I try to do opacity expansion, I can do it at least to first order. But what I would really like to do is to really calculate that path integral with these things. Okay, and people have worked very hard on this. And fairly recently, people have come up with a scheme. So that's what was missing. People have come up with a scheme that actually resums the full set of medium interactions with a realistic potential. So this is contained in those 2 papers there. I have nothing to do with this, okay? And you can see very cute things, okay? So this full calculation, so here done, so in this case with Yukawa potential, okay? They don't have the plot that I wanted in the paper. It's this beautiful red line. So this is just the spectrum by energy. So it has been integrated over transverse information. So there is, it's not actually, oops, oh, it's not this one. It's not actually this formula, it's this formula after integrating over this momentum. So it only depends on the energy of the related gluon so that you can draw nice plots, okay? And here he's been rescaled by some scale, okay? So in this case, so this N0 times L is a measure of the opacity of the medium. So how many scattering centers you should encounter in I was going to say something very stupid. How many you should encounter during the extension of the medium, okay? So the full calculation is the line. The opacity one, so opacity one shouldn't really work here, and we see that it's very, very far off, except in the limit of hard emissions. They are rare. They should be generated by like a single effective scattering. So get it absolutely right. So good, always good that the limits work. The harmonic oscillator, okay? The harmonic oscillator is this thing called here, funnily enough, low energy limit. Okay, so this should be right for the emission of soft gluons and completely wrong the other way. And that's exactly what happens. It's never exactly right, which is a bit disturbing, but it's not too bad. Okay. Now there is another another line here called harmonic oscillator plus NLO. Okay, people like to come up with names. So what is this? This is the so-called, it's from the competitors of this paper. So, okay, so it's the so-called improved opacity expansion, which is something rather clever that does opacity expansion on top of the harmonic oscillator solution. Okay, and you see that this kind of only really works wellish in this region. Okay, so it's like complementing the harmonic oscillator calculation with something that takes into account the opacity, and it works but fails here in an intermediate thing. So just for comparison, this is what you get from this Yukawa calculation or a hard thermal loop potential. Okay, and you see that even in that case, I mean, there's quite some differences between the dashed lines and the full lines. Okay, all this to say that you actually can do quite well with these calculations nowadays. But now comes the question that I posed yesterday: is what can this calculation be compared with? What is the experimental measurement that I can do that will tell me you are right, your calculation is right, or your calculation is not absurd? Okay, so I have three suggestions. One is that we compare this to the suppression of the most energetic hadron in an event. Okay, so the most energetic hadron in an event, remember that calculation that we did is a partonic calculation. There's no hadrons there. There's a quark that radiates a gluon, and then it's a quark. Okay, so probably I should, so the radiated energy of the gluon is the energy lost from the quark. So probably I can compare this with leading hadron suppression, assuming, and that's not a bad assumption at all, that the leading hadron always emerges from the leading parton in some branching sequence. It's a fair, it's not an equivalence, but it's a very fair starting point. Okay, so what's the problem with this measurement? I'll have to put some form of hadronization in my calculation, or invoke some magic powers, and I'm not going to chant in any form. Okay, invoke some magic powers to say that a parton becomes a hadron and that's it. Those magic powers are called local parton hadron duality, and don't really work that well. Okay. So whatever I do, I'll be very sensitive to non-perturbative hadronization effects. So somehow that will put a huge uncertainty in my calculation. Okay, including possible modifications of how things hadronize in vacuum and how things hadronize after going through a plasma. Because hadronization in the models that we have in Monte Carlos are always extremely reliant, and for good reasons, in how colors are connected. So what are the color objects? I want to build objects that are colorless, so I have to pick colors. If those colors have been scrambled by having gone through a medium, I'll hadronize differently. There was a plot I showed, which now feels many days ago. Okay, so yes, this is a measurement that you can compare with, but there's a lot of caveats. Okay, these caveats are the main reason that jets were invented. I mean, the idea of inventing jets, which was done in E plus, E minus collisions a long time ago, is that you are much less sensitive to hadronization effects. Although what you are collecting are hadrons, you are looking at quantities that kind of are much more inclusive. So you dilute all these non-perturbative corrections. Okay, so you could think, can I use this calculation to look at jet suppression? Okay, jets are composite objects. that have to be reconstructed and defined. What do I have to do to use this calculation to compute jet energy loss and therefore suppression? I need to do a bit more work. I need to keep my angular dependence, because not all energy radiated from a parton is energy lost for the jet. Whatever I radiate inside the cone I didn't lose. Only what I radiate out. Okay, so that's a big difference between jets and hadrons. So somehow I have to even implement in my calculation a sort of a cut that implements my jet reconstruction algorithm. Okay, it's a theta function, so don't worry about it too much. Okay, so if I have that, I can claim that I've calculated jet energy loss to okay, what you call leading order or next to leading order, it depends. So, but to leading order, meaning one gluon emission. So I've calculated that. Okay, if I wanted to do to what I'm calling next to leading order, I would have to consider 2 gluon emissions. Okay. Actually, there's some advance there as well. You can resum all medium-induced gluon emissions. Okay. But to do that, you have to assume that there were no vacuum-like emissions. So that for invoking some magic powers, you switched off the vacuum physics. So again, it's not a very full calculation. Okay. So another thing that you can do is that you can compute the jet profile, or what sometimes people refer to as jet shape, which is just the distribution of energy within a jet or within a sample of jets with respect to the jet center. So again, you need angular information, and you can claim that with something like this, you calculate it to leading order in perturbative QCD. Okay. So from this thing that my calculation is good for everything, that should be able to give jet suppression and give hadron suppression, there's kind of almost an immediate consequence. Of course, the things will be different because one, I count everything that was radiated as out, and the other one, I count only something that was radiated far enough as being out. But in none of these cuts, the final PT plays a role. Okay, or if you want, the initial energy plays a role. What I radiate from a gluon, from a quark, the energy of the gluon depends very, very weakly on the energy of the incoming parton. It's very soft with respect to it, but it's not, there's no, just because I have more energy, I'm more likely to radiate. It's a logarithmic dependence that I didn't write anywhere, so shouldn't be mentioning it now. Okay, so this should be true, that the way that the suppression goes should be similar. The dependence on PT should be very similar in hadrons and jets. Okay, so hadrons should be just like jets, or jets just like hadrons for that. Okay, I want to keep that thing on top. So we could continue along these lines. So we can think of many, many observables. I'll write some on the blackboard at some point. We can define many, many observables from a jet. And every time I want to calculate a new observable, I have to do a new analytical calculation, okay? Or at least change my analytical calculation somehow. So those calculations increase in complexity with the complexity of the observable that I define, okay? So for instance, if I wanted correlations between two particles in the jet, I have to think very well. So two particles in the jet, I need to write a full correlation function for my quark and gluon at leading order. It's a more complicated calculation than the one that we did. Okay, so this gets tougher and tougher and tougher. And it's here that becomes wise to think about event generators. Okay, event generators do exactly what it says on the label. They generate events. Okay, so they don't calculate observables. They generate events. Okay, and then whatever your favorite observable is, you calculate that from the output of the event generator. So it's you in principle calculate all observables. Okay, so sometimes people say, oh, so the event generator is a bit giving up, right? I'm not going to do the real calculation. Any decent event generator really must reproduce the analytical truth in the limits where that analytical truth makes sense. Okay, otherwise it's just a glorified random number generator. Okay, which can also work. Okay. Another thing that for me is very important. So this is full of opinions today. Okay, so don't take it very seriously. That good event generator, the physics content of that event generator should be very transparent. You should know exactly what it's in. Might be complicated, but you should know what's in. And you have fabulous examples in the proton-proton world, something like Pythia. I mean, you can open the manual of Pythia, which is not a manual for a computer program, it's a manual of physics, and tells you this part of the event was modeled, this and this and this and this and this. If it's like the Parton shower, it's QCD. So it's not really a model, it's an implementation of probabilistic implementation of analytic equations. If it's hadronization, it's a very clever model. Okay. Then, so there should be no black boxes. I mean, always be suspicious of Monte Carlo event generators where you have no idea what's happening, or where it's impossible to have an idea of what's happening, where there are parts that make things that you don't understand. Very important thing is that event generators must be validated, or if they have tunable parameters, that should be done in some data set, and that data set becomes irrelevant after that. And then you only use it for different data sets. So for instance, Pythia has nothing to, or now it has something to do with heavy ions, but Pythia was entirely tuned in E+ E- collisions. Okay, and then it's used at the LHC. This tells a lot of how solid a tool it is, that it survived all that. Okay, event generators have another advantage is not a right word. Another nice feature with relation to analytical calculations. In an analytical calculation, whenever I want to include some physics that I know it's relevant, but it's a bit outside the box of my setup, I have to rethink everything. So here I'm thinking of tracking the evolution of the QGP in my analytical calculation, together with my development of radiation. No one really knows how to do this. Okay, it's a very complicated thing. So you go to an event generator, and it might be much easier to implement in some effective way that still makes sense those new contributions that you know are important. And if you are not very sure how to model it, you should say so. I'm not very sure, this is what I implemented, and this is a possible fragility of my model. So I'm not sure about this part. Okay. Another thing, and that's a real bonus, is that event generators make comparison with experimental data much, much easier. Because basically you are making a fake experiment, okay? So all these things that always change your theoretical predictions, like saying, we only measured jets above 25 GeV and only included particles that were above 300 MeV and in rapidity, all these things to implement these are all theta functions with integrals in our my analytical calculation. These are all cuts. And some of these cuts have huge effects, distort spectra, for instance. So in a Monte Carlo, in an event generator, you just say it, right? You just, when you construct your observables, you do exactly what the experiment did. This would be even easier if experiments always behaved and put their analysis on something called rivet that you've heard before. So that theorists or people running simulations would never have to worry. Everything that would be needed to reproduce exactly the experimental analysis would be in a code that I just, instead of giving it real data, I give it Monte Carlo pseudo data. Okay, so that's the, well, we'll come back to this. So, two very different event generators for jets in heavy ions, okay? Because I'll be talking about computer programs, the best place to do this is the blackboard, okay? So you have something called Joule, which apart from being a pretty name, stands for jet evolution with energy loss, okay? So people are very, I'm not a developer of Joule, I've used it a lot and enjoyed. So Joule, and the other thing I want to talk about is this weak, strong coupling hybrid, okay? So this one I've been actively involved, okay? So I want these two things because it's two cases that I kind of understand, and because they are very, very different, okay? So what is different? What is understood to be the QGP is already very different in these two cases, okay? In this case, QGP equals best hydro simulation we can find. Okay. Okay, that's, and for us, best hydro simulation we can find is a function which is a local temperature. So a temperature at some space-time position. Okay, that's the information that enters in this Monte Carlo. Okay. Here the QGP is the same thing as that side, but not quite, okay? Because of what comes next. So the QGP is a distribution or it's the same T or energy density, it doesn't matter. Which is used to compute a probability of finding a scattering center. Okay, there's many people here that work in hydro. What's a scattering center in hydro?
In transport, you can actually do evolution of QGP in transport because there are quasi-partials.
In transport, yes. In a hydrodynamic evolution, there are no quasi-particles. And we actually believe that the QGP has no quasi-particles, right? That's why it's a collect. Okay, so here, this thing is used to compute the probability of finding a center and determine the form momentum of the scattering center. Okay, so this builds a perturbative picture. So I find things in the QGP, what I call the QGP, with which I will scatter. So it's a direct implementation of that picture that I have been selling, right? That I exchange soft gluons with something that was the QGP. Okay. So this is not quite true. So could be any good hydro. Okay, there's no limitation to use that. But if you just install Joule and run, what your hydrodynamics is 1 + 1 Bjorken. Okay. So that's the default implementation that comes with it. It's a separate part of the code. So, okay. So here, this assumes the existence of quasi-particles. Here, interaction between propagating parton and QGP is something strongly coupled. So it's certainly not something that I draw in a Feynman diagram. Okay. So this interaction here with the medium gluon, okay, is done in PQCD with some infrared regulation. Otherwise, this cross-section, when this exchange is 0, would just diverge, okay? So the infrared regulator is one or the tunable parameter in Joule. It was tuned once 15 years ago. Just making sure that your cross-section doesn't go completely bananas. Okay. So here it's more or less clear what will happen. So everything in Joule is, so interaction with medium is a 2-to-2 process. Okay. That's how it interacts. Here, interaction is something strongly coupled. I don't know how to calculate strongly coupled things. So this is calculated with a holographic calculation in ADS5. Okay, I'll show a picture of how this works. So each parton there interacts with the QGP through some dual computation done by holographic methods, which just gives you dE dx. So where x is the distance traveled. Now, here, I need a parton shower. Okay, I need how to make the breakups. So this starts with PTS6. So well-established code. So this is virtuality ordered. So your shower high virtuality to low virtuality until a scale where you stop because things become on shell. And how is this modified? It's modified in the following way. I have a propagating particle. How long will it take for it to split? Okay. So this is done by standard Pythia-6 methods. There's a Sudakov form factor, right? There's a thing there that tells me up to what scale I'm not in Q squared, I'm not going to split. Okay, from that I make a time. I convert to a time and I say, okay, my splitting will happen after some tau. Okay. I would have this. Nothing happened yet. Okay. And then I ask, am I going to see a scattering center? Am I going to interact with anything before that happens? If the answer is no, then this happens. If the answer is yes, I scatter with something. Okay? I scatter with something, which means that my momentum is now different. There has been a full momentum exchange, right? So now at this point, I see with this new particle, what is my formation time? How long does it take to split? And I can have one of two results. After or before. This one that I had before. Okay? If it's after, I don't care. If it's before, I replace this by some tau. And now I'm going to, this is not going to happen because something will happen before. And then I ask, so up to this time, am I going to see another scattering center? And the answer is yes. Okay, and I do the same thing, and I have a, okay. So what have I done here? I've implemented the LPM effect in a probabilistic way, because I'll have many, I can have many interactions with the medium that result in a single emission. Okay. Now, something that's confusing historically is that the splitting function, so what will be the splitting, is still the same as in vacuum. The splitting occurs in vacuum, okay? Or occurs as if in vacuum. What has been changed is when it happens, okay? Important piece of jewel. There is a justification for the splitting itself not being modified. The vertex function is that this is a very local quantity. Okay, so this is how this is done. This has been checked in the very beginning that it conforms both to the opacity limit and to the harmonic oscillator limit. So reproduces what were at the time the known analytical results correctly. Okay, so this is the construction in Joule. Nowadays you have an option which is, it used to be that you never cared about these things. Okay, they did their job of scattering, and you didn't keep them. Okay, now you can keep this as well. See where it ends up, and it might end up inside the jet. So that's a medium response contribution to what you will call a jet at the end. Okay, so this is kind of the thing of Pythia. So what are the parameters of Pythia? Is that infrared regulator, okay? It's the d by mass of these particles. It's not really a parameter. The value of alpha s that you take, and how many flavors you take it. So there are no free parameters. Okay. Then there are parameters that are. So it also, of course, geometry correct. So the production point is sampled from the overlap function of the nuclei. Okay, so the distance that some particle is going to travel in the QGP is an event by event thing. Okay, so that's kind of almost trivial that if you don't do this, you'll get wrong things. Okay. What else needs to be said about PTA? About Joule. Very important thing. Joule actually what it simulates is a nucleon, not a nucleus-nucleus collision. It's a nucleon collision. So typically there's only one hard one in real life, so that's fine. Which means that it doesn't keep track. So my output, okay, which is a HepMC file, so with lists of each event, all the particles in the final state, does not include the hydro background. So if you want, it doesn't include the result of all the other n participants -1 or -2 interactions of nuclei. Everything that is soft was modeled by some input, and it does not appear in the final state. So this is not a full event in that sense. Or you can say that it has been exactly subtracted for background. So it's if experiments could subtract the bulk background idea perfectly, this would be comparable with that. Okay. I'll talk about that in the next line. Okay. Because that's tricky. Okay, so this model is different. It keeps everything. Okay. So in this model, what is done is it's hybrid. I don't know if you like the word hybrid or not the word hybrid, if it means Frankenstein or okay. It really does a hybrid thing. So the main assumption in this model is that physics at different scales should be treated differently. Okay, and there's two very distinct scales in the interaction of a jet with a QGP. One is the jet development, okay? And think in vacuum, okay? Because no one switches off vacuum physics. This is a very violent process that happens at high momentum scales with high momentum transfer. So that is really a perturbative process, okay? And then the medium is strongly coupled, soft, and the interactions with the medium are soft. So we treat these two worlds separately. There is perturbative jet showering or pattern showering and non-perturbative interaction with the medium. How do we do this in practice? It was nice, right? So we get PTA8, okay? Doesn't really matter. It would work with that as well, but this was developed substantially later than this, so PTA8 was already the standard. And we generate in vacuum, okay, which is what PTA8 did at the time. In vacuum, we generate events, just hard events. So just events that have typically two jets and no multi-particle interactions, so just the hard part. So we get, okay, something going one way that I don't care here for the moment. And I get, what I get is a list of particles, right? But since I have access to the event generator, I actually keep the entire tree of what Pythia did, how Pythia went from 1 to 16. Okay, I keep that. No, this doesn't look right. Okay, so I keep this entire tree. Okay. So what an event generator gives me for this thing is that it gives me the 4 momenta of each one of these. I have a triple vertex here that shouldn't exist. I think that's fine. Yeah. Okay, so from those, with that information, I use my famous estimate of formation time to give a time for each one of these vertices, tau 1, tau 2, tau 3, so on and so forth, okay? So what do I get with this? I have a space-time picture of how my shower happened, okay? So I know what happened when, okay? I take this shower as is and embed it in hydrodynamic things. So I do the right thing of the origin points, the geometry, fine. Then, so I put this inside a QGP, okay? And then the only thing I do is that I go back to the beginning of this and say, okay, this traveled for a time tau 1. This is the time after which this guy split. So I'm going to make it lose energy for having traveled a distance tau 1, okay? In that distance tau 1, the temperature is changing because the plasma is expanding. So I have to integrate over that path. And what that tells me is that I would have lost some energy from here to there, okay? I use that loss of energy calculated holographically with a funny formula to rescale my 4 momentum. And then I do something very naughty, okay? I say, okay, this meant that my momentum here is not the same as the momentum there. But these are not massive effects that would change the way that I would have split. So I'm going to split exactly the same way. So if the division of energy was 10% or 10%, 90%, it would still be 10%, 90%, just with the reduced input. So what I'm doing by this procedure, and I keep on going, what I'm doing by this procedure is that I'm depleting elastically. I'm just taking energy from these legs, okay? I can get rid of legs if my energy is completely dumped into the QGP, okay? So I might lose branches. I might lose, for instance, this branch, because I lost all energy here. So with this, what have I done? I've lost energy from all the constituents of the jet, and I've also changed the structure of the jet, okay? Because I got rid of things. Now, what happens to the energy I lost? What happens to these guys I scattered with? So this is, we enter the realm of so-called medium response, okay? So in Joule, it's very simple. In Joule, this happened, okay? So you had a parton from the shower interacted with something from the QGP, okay? Call it P1, P2. This went there, this one went there. 3, P4. So this might end, nothing else happens to this, okay? Goes straight line. So I might end up in the end reconstructing this thing inside the jet. Okay. But that's not, there's something I need to subtract, because experimentalists always subtract what would have been there if there was no jet. And this particle in Joule would not have been there if there was no jet. What would be there if there was no jet was this one, right? That would just have gone. So somehow I need to devise a method that I reconstruct this, but I subtract a whole that is what would have been there if there was no interaction. Okay, so this is a bit intricate how it is done, but now works. Okay, here it's completely different. Right, but if you put if you do it like that, you end up having like negative jet masses in some cases, negative mass squared. So a really good a really good score, right? So you need to, what you do is that you subtract this not entirely locally. So if it's just for PT, you can do exactly what you, but for substructure, you have to be careful. So you subtract it from nearby particles using the ideas that come from constituent subtraction, which is the preferred method by the experimentalists as well. Here in a very peculiar implementation, but it works very well now, okay? So here it's completely different. So here what you have is that each one of these propagating legs dumped energy into the QGP, which is a hydrodynamical system. So what it does is that it locally excites that QGP. Okay, it's a small correction to this enormous bulk evolution. So we treat it linearly, which means that we then make that deposited energy evolve hydrodynamically, separately from the rest, and we add it at the end. Okay, patient is awake. It's just I'm depositing in a direction. I'm creating a wake like a boat does. Okay. And this wake, part of it will end up in my reconstructed jet. And that part I take as a contribution to the jet. I make it into particles when I need to and all that. So not all energy lost in both cases, even like this, not all energy that we think is lost to the QGP is actually lost from the jet, if you want to compare to data. Dime.
The hybrid model, you are taking into account energy loss, but you are not taking into account this radiation.
No, so in the hybrid model, there is no medium-induced radiation. It's stated very clearly in the label, in the papers. Yes, there isn't. Okay, so I think I've kind of made the distinctions. Then there is a funny thing. Both these models actually describe data very well, apart from details. And the ideas are almost dysfunctionally separate. So let me just show you a few things. Okay. We had that, going back to the observation that according to our calculation, jets and hadrons should lose energy exactly the same way. Okay. Do they? Not really. If you look at RAA, at jet suppression, so this plot is actually, so most of these things are now known to higher energies, but no collaboration has bothered to make a plot where they actually have all the most recent data for hadrons and jets on the same thing. So I still use this one that is 3 years old, but okay. So RAA so RAA is just the ratio of cross sections, so the suppression. RAA for hadrons grows with PT. Let's forget this very short region, which is potentially very complicated. It grows and keeps on growing, and it goes. So if I continue this is something like that, approaching 1. RAA of jets, on the other hand, grows and then flattens out. with very, 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 very tiny PT dependence. So this really flattens out here. So they are very different. The dependence on PT is very, very different. So there must be something beyond our analytical calculation that explains this. Okay. Okay. So now João gave a talk about what I had to say here, and I don't want to extend the time today too much. So I'll skip this discussion. That actually we are always doing the wrong thing, which is to compare jets that ended up the same and not jets that started up the same. So this is, let's go forward. Okay, and back to the same plot. Okay, so what's the difference between jets and hadrons that make them be suppressed differently? It's a simple answer, but in my opinion, rather non-trivial, because it's not the sort of things that we usually think. So this is the advertising picture of the hybrid model, because I'll get to the conclusions about the different suppression of jets and hadrons in the hybrid model, although it's generic. So what we do in the hybrid model is that this is our real theory, that everything happens perturbatively. Okay, we don't know how to do the calculation of the interaction non-perturbatively, so that we do that on ADS5, where this energy loss is just a string that falls towards the direction 5, where there is a black hole that is the temperature of the system. Okay, I don't know how to do vertices in these calculations. Things don't split. So what I do is that I imagine that there's a vertex that is the one that came from the lab. So this is a bit of an art. Okay. Just the formula, this formula that I did not write here, is something that depends on the incoming energy. But the really important thing here is this X stop. So perturbatively, a propagating quark never loses all its energy. It's not possible, or loses all energy in an infinite medium. Here, this happens often. This formula has a Bragg peak. So energy loss grows first linearly, then squarely, then becomes non-polynomial, and then it's complete. Okay, and this is extremely efficient. If you look here, for particles that are soft. They have low energy, they are more likely to be stopped anyway. Okay, so this model only has one parameter. The hybrid model only has one parameter. Okay, which is, so this formula is computed by string theorists, or whatever. Oh, actually, they are not string theorists, but this formula is computed holographically, where X stop is defined like that. And if you are doing the calculation in super Young mills, which is where this calculation is done, n equals 4 super Young mills, then this K is something that is related to the number of degrees of freedom of the theory, and it's for all purposes equal to 1. Okay, so what we decided when we invented the model was to leave this as a free parameter, because we are not using this in n equals 4 super Young mills. We are using this in QCD. Okay, so QCD has a lower number of degrees of freedom than super Young mills. So this number should be smaller, but of order 1. Okay, if this number had come out, so this is our fit parameter. If this number had come out like 0.01, forget. If it was 20, forget. Okay, so 10, forget. Yeah, so it's the free parameter. Okay, I'm not going to go into more details of the thing. So in in the beginning of the beginning, we fitted that parameter to a single data point, which sounds like a very strange procedure, because there was very little data at the time. So we fitted fixed that value from one data point, and then use the model to predict the other data points. Okay, now it has been globally fitted to lots of data. But remember, what you fit, you don't predict. So it's okay. So what did we do here? We just took the model, okay, and computed the RAA for jets and hadrons. And we get it very nicely, okay? So actually, if we extract the K value from each thing of data that is available, it gives very consistent values, okay? Except for RIC, that is always off. And this has been observed by many people, that there is a tension between LHC data and RIC data that is not fully understood, okay? The QGP, one way of interpreting it is that the QGP at RIC seems to be hotter than what one would have expected, if you want this. So we have this excellent fit, and then we said, okay, our model gets this right, but what in our model makes us reproduce jets and hadrons differently? So a hadron is a hadron. Very approximately comes from a single parton. A jet is a composite object, where in any of these models here, each parton propagating is a candidate for energy loss, right? So my energy loss of the jet is not the energy loss of one thing, it's the energy loss at each instant of time of how many things there are in my tree, okay? So energy loss is kind of proportional. I'm not saying what's the power, proportional to the number of constituents. So how much a jet broke up, okay? And what drives a jet breaking up? Actually, it's the initial virtuality of the parton. It's vacuum physics, okay? It's the first splitting, how big it is, that will tell me how much space I have for the others in phase space. So it's actually something that is driven almost exclusively by vacuum physics. So now notice something. So when I say I reconstruct a jet with 100 GeV, I'm completely agnostic if that jet has 2 particles or 50 particles, okay? So it could be something that fragmented very little and something that fragmented a lot, okay? Now, if I impose that I want with 100 GeV, that hadron belongs to a jet, right? A hadron with 100 GeV, how could I get it? Well, I could get it from jets that, or it can be part of a jet that has a bit more, but fragmented very little, right? But this is really the dominant thing. Or it could be, sorry, or it could be part of a jet of 500 GeV that has lots of things. But jets of 500 GeV with respect to jets of 120 GeV are highly suppressed. The spectrum falls with PT to the -5, -6, whatever. Okay, so when I require a hard hadron, I'm making a selection on the family of jets that I'm considering, okay? So I'm privileging jets that fragmented very little. Jets that fragmented very little have fewer legs, so they would have lost less energy. So I've selected the population. Okay, so that's the conclusion from here, and we did an important check, which was look at the jets that contain the hadrons that we were including and seeing the suppression just of those, and the suppression of those matches exactly the suppression of the hadrons. Okay, so our calculation is not wrong. Our initial calculation, applying it to jets and to hadrons, is just that when you compare with data, you have to be very, very careful in what you select when you make a measurement. Okay, so this will appear in any model that treats jets differently, or treats jets as jets with something that has internal structure, and where this dependence on the number of constituents is part of the game. So I lose energy more if I have more things. Okay, let's get this. So this is a very important lesson, is that the QGP sees the internal structure of jets. Okay, the QGP does not interact with the jet as a single object. It really sees the internal structure. And this is a very bizarre statement, okay? Because quarks and gluons are not asymptotic states. So you are not allowed to see them as such. Okay? So for instance, they can never be seen in a detector. No matter what's the resolution of the detector, they are just not physical asymptotic states. So the QGP actually allows us to see partons because it is seeing the partons, it's interacting with them. Okay, so you can see this the other way around, that this branching sequence actually resolves and sees the QGP. Okay, so this is it's the current trend that you'll hear in many, many talks, that one looks at substructure. We can look at the spatial temporal, so we look at substructure to see the spatial temporal dynamics of QGP. So this, another slide is that, so this is what we saw. And so I need to make this difference. So what I said, that jet quenching really depends on the branching width, so how rich my shower is. This is almost dictated exclusively by vacuum physics. The first splitting in a jet is always before there is QGP. So actually, it's a statement that many people don't like, is that vacuum physics is the main driver of how a jet gets quenched. Okay, sounds a bit silly, but it's true. Okay, this is our calculation again, written in a more schematic form. So this is what you get if you do the calculation for the harmonic oscillator thing. You don't get the K anymore. You can write it as a sign. Okay. So if I want to evolve in the world of analytical calculations, I should now consider the coherent emission from more than one emitter. So the so-called QCD antenna. Okay, so the easiest place to do this is to look at a QQ bar pair. Okay, and then in vacuum, this is pretty simple. The calculation is not simple, but the conclusion is pretty simple. Is that I have two scales. I have the transverse separation of the QQ bar pair at the time that the emission occurs, at formation time. And I have the wavelength of the gluon I'm going to emit. If the wavelength is larger than this distance, then this gluon cannot resolve the two legs that are emitting separately, and the emission occurs as if it was from the total object, which in this case it's color-neutral. So in this case, there cannot be radiation with wavelengths that are larger than the separation of the legs. Okay, this is what happens in vacuum. I can translate this into angles. So this tells me that there is no radiation out of that cone ever. It's not possible. Okay, this is the angular order in QCD. Of course, if this was a gluon, then it's possible, but it's suppressed with respect to the legs. With respect to things inside. If you put this inside the QGP, now I have another scale, okay? which is the scale introduced by the medium. Okay, so it's another scale. If I want to make it into a distance scale, it has to be related to the inverse of the transverse momentum acquired by traveling in the medium. So it's 1 over square root Q hat L. So once you cross this scale, what happens is that the QGP, the interactions with the QGP have decorrelated your two legs. So it means that these two legs are now, for all purposes, separate. They don't know about each other, so there is no coherent emission anymore. So I can write this in terms of a time scale. How long does it take for the two legs to decohere? And this, if you go to the strict soft limit, of course, the real situation is somehow in between. You have a clean separation between what's vacuum-like radiation, that it's all inside the cone, okay? And all medium-induced radiation is all outside the cone. So it's anti-angular ordered, okay? So that's a very, very non-trivial result. So people built a very intuitive picture that hasn't been properly formalized, but it's a very intuitive picture that kind of makes this, refines a bit this picture of the number of things interacting with the QGP. So whatever I have inside my shower, I should not count the number of things, but the number of things that can be seen separately by the plasma. So the number, because if they are too close together, they will just not be seen separately by the plasma. So they interact with the plasma as a single thing. Okay, so it's this picture here that actually what is relevant is the number of resolved colored charges in a sequence like this, no matter how you build it. Okay, so this is a very nice picture in my opinion, and so many people here know Carlos Salgado. He draws very, very nice pictures, and this his picture of what happens in a parking shower is that you have all these things and everything is happening at the same time. You have vacuum-like things and medium-induced radiation, but they really live in different planets. Okay, everything that is vacuum-induced, vacuum-like, is inside the relevant cones, and everything that is medium-induced is not collinear at all. It's just high angles. That's why you actually lose energy. Okay, so this is the thing. Now so what I'll do is that I'll not stop. It's too late to stop, okay? And I'll finish as early as possible so that we can then enjoy ourselves. Okay. Now, I have a very important lesson. It's a lesson that I learned myself, okay? And I think that it's important to share. So I always share it, okay? Which is going to very simple observables, okay? So the first observable that was measured for jets at the LHC, so the first observable that was measured for jets in heavy ion physics. So the first measurement is from 2010, but this has been remeasured, and the measurements are still a bit puzzling sometimes, is the so-called dijet asymmetry, okay? So most jet events are dijet events. I have a jet back-to-back with another one. And something I can calculate is the difference of their transverse energy, transverse momentum, and if I wish, normalize it by the sum. Okay. So at partonic level, the two things were born with the same transverse momentum in the hard process, right? So that's just momentum conservation. So if I'm just calculating 2-to-2 matrix element that produces my mother partons that I'll get jets from, asymmetry has to be 0. Okay, there is no asymmetry. Okay, so this was the first thing to be measured because lots of uncertainties cancel in this ratio, whatever, okay? And the observation was very clear. Don't pay attention to details of the curves. There's only two things that matter. For central heavy ion collisions, the asymmetry was shifted substantially. So this is PP, or PP is the balls, okay? And the field balls are lead, okay? The distribution was shifted substantially to the right, so jet pairs were made more asymmetric, okay? So why are they asymmetric in PP in the first place? Well, because I don't catch all energy. If a shower is broader, I catch less energy, okay? This is radius 0.4. A shower typically goes up to 1. So there's stuff outside. And I can also have 3 jet events. So which is just a lot went outside. So 1 jet became 2. I only look at the 2 that are closer in angle. So I lost this. So already in PP, this is not always 0, but it's peaked at 0. And in heavy ions is not, okay? And the effect seems to make sense because it kind of disappears if you go to more peripheral collisions. Okay, fine. Then, another observation, which is a null result, is that the azimuthal correlation, so the angle, the relative angle between the jets, right, is not modified. You increase the asymmetry in energy, but you don't make them wobble. Okay, it's 2 observations in 1. Okay, so if we think of the BDMPS calculation, the single gluon emission, actually the most efficient way of losing energy is to radiate one of few fairly hard gluons. It's much more efficient than radiating many soft ones, okay? If you radiate anything with any hardness, you should deviate your mother charge by momentum conservation. So first lesson is that, First lesson is that the semi-hard rare emissions that are the driving mechanism for hadron energy loss are not the main mechanism for jet energy loss. So together with these 2 people, we came up in 4 days, okay, with an explanation. There's a danger of doing things in 4 days, which was, all that is happening is the peeling off of soft gluons. So soft gluons get the same wobble as everyone else, okay? But if I'm 100 GeV and I get a kick from the medium of 1 GeV, who cares? If I'm 2 GeV and I get a kick of G, I'm not here anymore, right? I'm there and I might end up outside the jet. So this basic idea is okay. And it really does not, because it's many soft gluons that were in different directions, I really don't decorrelate azimuthally. Okay. So nice idea, nice picture, okay? The paper is actually the picture. That's what you can do in 4 days. And that picture was it's too nice, okay? Look what happens there. That picture strongly suggests that there is one jet that doesn't lose anything and the other one loses everything. So if they started the same, I'll increase the asymmetry, right? Okay. So in part, this picture was responsible for this picture of asymmetry grows because one of the pairs loses none or much less energy than the other. Okay, that has to be true. But there's another problem with this picture. How typical is a production point at the edge of the overlap region? Certainly much much less likely than one here, or here, or here, or here, or here. Okay, so this picture has that bias. Okay, so, and this bias puts in our head and in everyone's head the idea that the most important thing for jet energy loss was how much path it travels. Okay, that jet energy loss is dependent on the path length, on the amount of matter I go through the medium. It certainly has to, right? If I see more matter, I interact more. But how important is it for this observable? Okay. The author of Joule and myself were playing with some things. And we're intrigued by several things and started making some things and and asked this question. Okay, so I know if I don't ask anything, I know where the production points are. Okay, it's just these are absolutely central collisions. Okay, let's make our life easy. Okay, it's really a circle, the overlap. So this is 0% centrality. Okay, so I know where my production points are. Density is there, the probability is. When I make a choice, I say I want to observe a jet with more than 100 GeV. Okay, there is something called surface bias. I'll be more likely to detect things that started closer to the surface because the other ones would have lost more energy, etc., etc. So let's see how big that surface bias is. So without asking any question, just where the production points are the red line. So this is the difference between the path of one and the other, okay? Difference between the two paths. So, and then, if I force the existence of an injected jet, yes, I shift, okay? I shift to the right. So yes, I'm more likely to see, I'm privileging things where the one that had more energy at the end traveled a smaller distance. That's what this shift tells me. Okay, good. My intuition was right. Except that of the distribution, about a third is the other way around in Joule. In about a third of the cases, the jet that traveled a larger distance in the medium, and this, okay, this is or the jet that encountered less matter, because this distance is already, it's an equivalent distance. It's not just a line. It takes into account how much QGP I saw. The ones that traveled more lost less energy. Okay. So there's something, so there was about a year and a half looking for bugs in the code, okay? There were none. So what's going on? Let's do an exercise. Does Joule actually, at that point, reproduce the dijet asymmetry measured in data? Answer is yes. The CMS data was were these black points, and Joule was the red line. So, I mean, it's not perfect, but it's fairly decent. Great. So it cannot be completely insane. Okay, to get this because it also fitted. Let's play an exercise. Let's, instead of doing this with the right geometry of where the particles are, where the jets originate from, let's create a imaginary, or no, a fantasy sample where all jets were produced right at the center. Okay, So there I forced the path traveled by the two jets to be exactly the same, no matter what direction they go. It's always the same. It's the radius, some equivalent radius. Okay, so let's see what that gives. Okay, so full geometry is the red line. All jets produced in the same 0, 0 coordinate in a circular geometry will give something that I would say is a bit similar. Okay, so there's something that we were interpreting wrong in the observable. Okay. So there's two effects here. One is that the typical events, so things that are produced mostly around these annulars actually, have path differences that are not that big, okay? Because the one that travels more in distance will start seeing more diluted QGP because it's expanding. So that's one effect. There's another effect. Is that really in this observable, the path length difference between the two. So I'm not saying that path length is not important. I see path length being very important in this observable if I go from peripheral to central collisions. I have more suppression, less suppression, okay? Or more shift, less shift. But the difference between the two is really not what is driving this. I mean, I've proven it. So what is? Is that jets are all different. With the same PT initially, so that's fixed in the thing, but the virtuality is not. The invariant mass of the pattern is not. So one goes that way, two goes to the back, have the same PT. One can have very high virtuality, the other one can have low virtuality. The one with high virtuality will split more, split much more, and therefore will lose much more energy. Okay, so again, it's this picture that there is a proportionality between amount of energy loss with the number of things inside a pattern shower. And that in this particular observable, it trumps the, you shouldn't say this word right now, it gains against what would be the effect of traveling in the medium. Okay, so no need to discuss this. These are all for us to be sure. The same conclusion obtained in calculations with the holographic jets. So, but actually using this formula applied to a complete jet and not to partons. And also in some analytical results that I don't know why I don't have here by Edmund Janku and etc. So actually it was our intuition that was really wrong. That we, oh, such a nice observable, it must be dominated by the difference of path lengths. So the lesson is always check. Never assume things like this. It's okay. So from this, there's another lesson, and what I think it's a very reasonable question. So from all I've said, and probably all that you've seen, I think it's fair to say that quenched jets share a lot or most of their features with vacuum jets. They're still jets, okay? There are modifications, and we have been looking at these modifications, quantifying, calculating them, but they are still jets, okay? And what is in competition in a quenched jet is this really violent process, which is jet showering in vacuum. Okay, it's a dramatic thing that goes from 1 TeV to GeV, few GeV, very quickly. Okay, to the QGP induced modifications, which are in comparison, small corrections to that. They are very important. We've been looking at them. We have seen them. We have described them theoretically, but it's an explosion with corrections. Okay. Now, with this, will we ever be able to tell things apart? Like, can I tell? I look at a jet. I'm given a jet, okay, which is a list of 4 momenta of particles. Can I tell? Did this go through the QGP, or did this not go through the QGP? Can I do that? Okay, I think it's a fair question. If yes, I can see that lots of distributions are shifted. Lots of observables are modified. But can I look at it and say, this is a dog and not a cat? Okay. So there's only one way to do that in practice, is to ask a machine if it can learn to distinguish them. Okay. So this is really my last words, my famous last words. Okay. Which is just, so this has become trendy. Yeah, it's the thing. Everyone does machine learning, right? Even if you don't. So with some people, and the other people are working this as well, there has been an effort to try to answer this question. Is there enough difference for it to be distinguishable? If there is enough difference, a machine should be able to learn. Okay. So I won't describe any of the details, okay? Because I want to finish at the hour, okay? To be fair and to, so they're not going through the details. I'll just go to the conclusions, okay? So here, this is work that looked at many architectures of machine learning that take inputs as different things. So jets were represented by images, okay? To use the technology of image recognition. They were represented as coordinates of the sequence of splittings, okay? For something that would be sensitive to the ordering in which things happen. Or they were done just with the minimal information, like what's the PT and how many particles does a jet have, okay? Okay, we did various things. The most important thing is that in all cases, there is a distinction, okay? Whatever the machine learns, which for instance in images is easy to understand, in those things of the sequences is a black box. Or for me, it's a black box. For all architectures, so images, we remove the information on the total momentum or not, okay? All of them can tell things apart. I mean, if I say I'm only looking at jets that have an output larger than 0.6 here, this is mostly jets that were modified. Okay, there's a contamination, there's some false positives. So what? Okay, but everything that we tried worked. This one looks a bit worse, right? When I get rid of the PT information of the jet, the results look a bit worse, but they are actually better. Now, so this is just a measure of how good your discrimination power is. If this was 0.5, it would be the result of a random thing. Okay, so any number above 0.5 is good. The more above it is, the better it is. Okay, and we have this, and we confirm that thing with images that were all normalized to the same PT do worse. Okay, but then you should do something. It says I trained this in some particular set, and then I verified it in a different set. But let's apply this in a completely different situation. Let me apply this for jets that were just, I trained this with all jets above 30 GeV, and I got these pictures. And I do it again for jets that are much harder to train. And I see how this works. So I see a degradation in the 3 good cases. I see a degradation of my ability to distinguish, except for the case where the information of PT didn't enter. Actually, it's very robust. So it might actually be better because it can predict things for which it was not trained much better. Okay, then we had to check that actually this was what it was calling a class A and class B, or positive and negative, more quenched than the others, because another lesson, a neural network or any of this stuff always gives you an answer. Okay, if that answer has anything to do with your question, it's a different thing. Okay, so we had to check, we checked, and yes, these things that are called quenched, or that are identified as the quenched category in the thing are more they are what they are. Yeah, and the ones that are identified as being vacuum actually are really vacuum. Okay. Yeah, you can look at many things. So then you can ask, if this is all so good, oh, this is funny. If this is all so good, how many observables? How much is enough? How much information do you need to make this distinction? Okay. Again, if you want details, you can email me. This is not published, so it's nice. So basically, you have we considered in this study 31 different observables for each jet. Okay. Took all these and then looked at diagonalizing the matrix and seeing, are there eigenvectors, okay, in very broad language? Are there directions on this space of observables that actually are dominant? And the answer is yes. And from 31 observables, you actually need something like 5 directions, which do not correspond to trivial observables, unfortunately, okay? But your complexity goes from, you don't need 31 observables, okay? And you actually can look at how much a single observable can do of your total discrimination power, okay? Or pairs of observables. And we find many pairs that have discrimination power of 99% as compared to the 31. So this is, okay, there's many caveats, but this could help inform what are the priorities for people to calculate and to measure. Because if you don't need to be measuring 31 different observables. You can probably focus on a few that contain as much information as all the others. So this is really a tiny detail. And another thing that seems to be very robust are correlations between observables, okay? So things like, I measure 2 different properties of a jet, I find a correlation between them, and this correlation doesn't change from vacuum to medium. What really changes is where this correlation curve is populated, okay? So like this, it's a correlation between 2 observers, I can't read which ones they are, okay, or here. And what has happened is that the shape is still the same. So the network learned that if this observable has this value, it's very likely or most likely that the other observable has this one. And this is unchanged. So these correlations between observables are built in stone. And what changes is how this is populated, okay, by the 2 samples. Even here, that looks like a blob. The blob is the same, but there is a migration of what is important in one case and the other. There's also some cases where these correlations are completely broken. So it's looking at those correlations is very sensitive to QGP effects. Okay, there's many caveats on this study, so don't take it very seriously. But it's, I think it's important to talk about these machine learning techniques in this context, because contrary to what some people say, it's not giving up on physics. It's really trying to simplify our life in deciding what is more relevant to do in the traditional physics way. This will never replace our ability. It's like ChatGPT will never write a proper book, okay, that people would enjoy in 10 years' time, okay? But this will never solve, this will never be a physicist. But this is essential when you have 200 observables that you could look at, to have a perception of how much will this contribute to the problem that I'm trying to solve. So that's, I wanted to finish there, and it's done. And I took 5 minutes too much. Thank you.